On-device 3D sensing is important in virtual reality, augmented reality, gaming, and navigations. Recently, direct time-of-flight, or DToF sensor, is attracting intensive interest in both academy and industry as a promising candidate for next-generation on-device 3D sensor. However, limited by manufacturing capabilities, current DToF sensors only provide low-resolution 3D data. To overcome this challenge, a high-resolution RGB image can be used as guidance to predict a high-resolution depth map before passing to downstream tasks. Previously, RGB-guided depth super-resolution or depth completion algorithms process the inputs per frame. Therefore, they suffer from the ill-posed nature of the problem. The predicted depth usually contains blurred edges and incorrect depth values or missing details. Also, when the depth prediction is performed on an input video frame by frame, the results are temporarily unstable. In this paper, we propose for the first time a DToF depth video super-resolution framework. By efficiently aggregating information from multiple frames, the proposed DVR-style network achieves high temporal stability as well as high depth prediction accuracies. What's more, DToF sensor provides unique histogram information. We further propose low-resolution histogram processing modules and integrate them into the framework to form DToF histogram video super-resolution network, HVSR. Spatial ambiguity in input is further lifted and fine structures are revealed in the depth predictions. In a DToF sensor, a laser diode emits a short pulse at time t0, and the pulse is reflected back from the same point and arrive at the DToF sensor at t0 plus delta t. The reflected light triggers a time stamping event, and there is a proportional relationship between depth and delta t. Each DToF pixel receives reflected signals from multiple scene points within the patch in the field of view. The signal is called a histogram. Multiple such histograms form a 3D data volume. The DToF sensor can operate in two modes. In the peak detection mode, only the depth value that has the strongest signal is picked out to represent the whole scene patch. In the histogram mode, the post-processing algorithm has access to the full histogram that contains more information. However, this also poses challenges on the computational cost. Our network follows a two-stage processing framework. The two key components are the multi-frame aggregation module and the confidence prediction module. To aggregate information from multiple frames, we utilize a flexible warping module that picks multiple candidates with deformable convolution operation. Compared to conventional flow-based warping, the flexible warping module is robust and agnostic to static or dynamic environments. To utilize the histogram information while maintaining low computational cost, we conduct a peak detection-based rebinning operation on the full captured histogram. With a predicted depth patch, we use the image formation model to convert it back to a predicted histogram, and by comparing the two histograms, confidence in the depth prediction is estimated. We train and evaluate the proposed network on Tartan-Air RGBD video dataset. The proposed algorithms achieve high temporal stability and also improves depth prediction accuracy significantly. Here's another scene from the Tartan-Air dataset. It is more challenging with more complicated lighting effects in the RGB video. While the per-frame processing network is confused by the textures in RGB videos, the proposed models remain robust. We conduct cross-dataset evaluation on the replica dataset, a real-world capture dataset with high-quality geometry. Similar comparisons on temporal stability and accuracy still hold on replica dataset. Previously, no large-scale RGBD datasets contain significant amount of dynamic objects. Also, high-quality synthetic DToF datasets are missing. We introduce DToF dataset with animal animations and physics-based DToF simulations. The dataset contains 100 videos with 45K frames. The DToF dataset provides various data modalities, including RGB frame, depth map, surface normal, albedo, and camera trajectory. We conduct evaluations on the DToF dataset and focus on dynamic objects. Although our models are trained on a dataset with very limited dynamic objects. They generalize well to dynamic scenes. We attribute this generalization to the flexible and fault-tolerant multi-frame fusion module. We propose consistent detail of video depth super-resolution algorithms that utilize multi-frame information and unique histogram information. We achieve significant improvements in temporal stability and accuracy. We also introduced the DiDTOF dataset, the first synthetic RGB DTOF dataset that features dynamic objects and a realistic DTOF simulator. Please refer to our paper for more details.